first. Okay, people are joining. Yeah, maybe let's wait for one more minute.
Mm-hmm.
Okay. So maybe let's get started. Hello, everyone. Thank you for attending this week's Paraelectric Chemistry webinar. I'm Bo Xiang from UC San Diego, and I will be today's host. So today, our speaker is Professor Angel Rubio. But before we start, I would like to introduce the schedule and the mechanisms for this webinar series. So our Paraelectric Chemistry webinars will be held every Wednesday at 9 a.m. Pacific Standard Time. For each talk, you must register to participate using the link provided here or the link we included in the reminder emails we send out every week. You could also follow our social media on Facebook and Twitter to check the updated status of each webinar. Also, we have created a Facebook group called Paraelectric Chemistry Online Community, where you can share recent findings, research papers, or other relevant topics here. So if you haven't joined us, you are most welcome to do so. So if you missed the live or would like to re-watch it, feel free to go to our YouTube video channel called Paraelectric Chemistry Webinars to see all of our recorded previous webinars. And don't forget to subscribe. And finally, I would like to explain the webinar mechanisms for the new attendees. So during the talk, you can use this raise hand button to ask questions, and I will interrupt our speaker at appropriate places and enable the audio for you to talk. You could also use the chat to discuss with everyone. You can leave the comments and questions there. And for Q&A, you can write down your questions, which will be raised by the end of the presentation. For questions that are not addressed due to a time limit, we'll collect them and send them to the speaker later. So you may find an answer from our social medias after the webinar. Okay, now let's move on to today's webinar. Today's speaker is Professor Angel Rubio from Max Planck Institute. So Professor Rubio was born in Spain in 1965. He obtained his bachelor and PhD degree in the University of Valladolid in Spain. And after that, he continued his worldwide research career of postdoc fellows and faculties in universities and or institutions in Spain, US, France, or Germany. And now he's a distinguished professor of physics in Basque Country University in Spain, a distinguished research scientist in the Center for Computational Quantum Physics in Simons Foundation's Flatiron Institute in New York, and also the director of Max Planck Institute for Structure and Dynamics of Matter in Germany. His research focuses on the modeling and theory of electronic and structural properties of condensed matter. And his team is working on developing novel theoretical tools such as time-dependent functional theory for quantum electrodynamics and computational code for ab initio description and control of the dynamics of decoherence and dissipation in quantum many-body systems, and also on characterizing new non-equilibrium state of matters. So today, Professor Rubio will give us a talk entitled Cavity Control of the Two-Dimensional Material Phenomena, Cavity-Tronics. So with all the introduction, let's move the stage to Professor Rubio's. So Professor, now you can share your screen.
Okay. Hopefully it works.
It's in a different mode. Yeah, now it's good.
Now it should work. Okay. Thank you very much for this kind introduction and for organizing this series of exciting seminars. I think it was a good idea that you took this leading role with Joel since the failure of the APS workshop last year and due to the COVID. I am very happy to give this seminar, and please interrupt me all over the seminar. It's not, we can do it more lively, in spite of the fact that we do it virtually via Zoom. Although the title is about 2D materials, I will basically address two aspects of this cavity control, which would be basically dealing with molecules and solids. And let me just give you a flavor of what we want to do and why now. But before going to the details, because I'm sure I will run out of time, I think it's very important to say who has been involved in all the work that I'm going to present at a given point. And then from the theory side, everything started with Michael Rubenthaler, Heiko Appel, and Johannes Flick, that is now in the Flatiron Institute and is moving to CUNY soon. And then on the quantum electrodynamics density functional theory. And then many of the results that I will show you are linked to the activities on the molecular side with Christian, Enrico, and in particular Enrico for the coupled cluster physics. And then on 2D systems with Simone, Sunsuke, Hannes, Umberto, Dombing, and others. And then I hope I will be able to address all the work that they've been doing. And then just not to conclude all the activity that most likely I will not be able to go through, which is these twistronic ideas of putting 2D materials in cavities, is done in collaboration with the people at the Flatiron Institute and with people now in Aachen and Martin Klassen that just moved to University of Penn and all the wonderful experimentalists at Columbia University. Then let me just give you a flavor of what we want to do and how, and it's more of playing with the game of this, let's call it quantum theater, in which we have to put as actors, not only the electrons, but also the ions. And now we want to add a new player, which will be the photons in our case. And then one of the arguments that why we want to do that is because we want to control matter or quantum matter and then change the properties on demand. And then I hope I will be able to convey that some of those aspects can be achieved with present technology and with present theories that we have. Then the aspects that we want to illustrate is how to reach new state of matters. In particular, you can say light-induced new topological states or other phenomena. In particular, when you bring these things into cavity, whether you can do modification of chemical landscapes and the chemical properties of molecular systems. There has been few talks in this series addressing different aspects of molecules in cavities. Then I will not repeat what has been said. I will give you a different flavor of what we've been doing recently on that. And then the aspects I want to address is the cavity materials, in particular to change the ground state of materials in cavities. This is something that I would like that you keep by the end of the talk. is that photons, or the cavity modes, will act as a bosonic glue, which is our glue that will change the properties of the material. And this modification goes not only with the excited states, which is a common activity in atomic and molecular physics, but also with the modification of the ground state of the molecular complex and material in the cavity. Then I will show you a couple of slides in how modifying the environment of the cavity, you can introduce new symmetries or break new symmetries in the system and introduce new phenomena. And the part that I'm 100% sure I will not be able to deal in detail, but I will just show you, is how you can bring this to the concept of cavity twsitronics and introduce more heterostructures as a condensed quantum matter simulator. And then there are many things that will be left open for the future, which I hope is brilliant, and then for many of us to keep working in it for many years. Then, to the sake of being repetitive, and something that you already know very well, is this argument of the polarity chemistry, which we call it light matter dressing of quasi-particles. Then basically, just to illustrate it, you have a molecule, then basically you're going to put it either in light or in a cavity with a frequency mode. Then the frequency can be tuned to either the frequency of the vibration or the excitation energy. And depending on where you tune the frequency, you get a vibropolariton or exciton polariton. And those are the main polaritons that has been discussed in one flavor or another during the last year in the series of seminars in these polaritonic webinars. However, we just recently did a nice exercise of looking what is the all polaritons that has been proposed in different flavors. And there are already 70 different types of polaritonic states, which is light matter dressing, which could go from the ones that we just described to Cooper pair polaritons, plasma polaritons, exciton polaritons, many others that you can imagine. And it's quite interesting to see the difference and similarities of all those polaritons. There is this article that we just got, and it's lively accessible in the web. Okay, then what I was telling you is this argument of having the electron hole pairs being glued by the polariton, and that's what will be the driving force of all the talk, is to use the photon as the glue. But before getting to that, there is some aspects that need to be developed, and is the theory underlying that description. And then, because we want to address new states of matter, we want to work in non-relativistic quantum electrodynamics. This is really important for what comes next. And then basically how we are going to do this QED chemistry and QED materials. Many of the things that I will present are introduced in the code Octopus, others are outside, and I will mention. Then the idea, I will have a couple of slides on the theory because I think it's important. You have different ways of approaching the system. One will be that I will show with the work of Henry Koch and Rico Ronca is the couple cluster approach, but another way to introduce correlations and electron phonon correlations in the material is by time-dependent density functional theory. And the only thing that you need to know is that there is a one-to-one mapping between a fully interacting electronic or electron boson system and a non-interacting quantum system. The advantages are clear, is that you need to solve, instead of an n-body problem, you just solve a set of n differential equations, which are non-linearly coupled. And the problem that is that you have to know the exchange correlation potential, which is a functional of the density, or in the case of the external field too. However, you ask why I am introducing this, is basically because this is not enough to deal with the problem that we are interested in. And then we have to address that with quantum electrodynamic density functional theory, which is a way to treat with fermions and bosons on the same footing. And then let me just give you 2 slides of what it is. And this is the equation that you've been familiar, because it has been presented in different flavors during the series of talks, which is you have the electronic part of the Hamiltonian, the interaction, and then the coupling to the cavity. And this is what usually is being done. And then the interaction between the cavity photons, or the photons itself, which via the current, and the external electromagnetic field. Then you have the standard equations of motion for the many-body interacting system, and the other one, which is nothing else than Maxwell equations in the time domain, which is the extension of the Maxwell equation instead for one photon for many photons interacting. And then just after a long analysis, you can prove the quantum electrodynamic density functional theorem that allows you to establish a one-to-one correspondence between basically electrons, photons, and some quantities, which will be, in your case, the current and the vector field or the transverse component of the photons in your system. Then basically this gives you a set of self-consistent coupled Maxwell-Conshan-Pauli equations that are the ones that we need to solve in this system. In this aspect, then I will show you two examples of application of these techniques, which is for chemistry and for materials. Let me start with the chemistry aspect. And before getting into the details, I will take something that is being shared by the perspective article that Joel and Vinod wrote about cavity-QED chemistry. And then one aspect which is important is the fact that you have this interaction between a molecule and a cavity mode. And then this interaction between the molecular and the cavity mode opens up a lower and upper polariton, which are split by width, which is proportional to the electromagnetic or the light matter coupling, which is usually small and give you energies of the order of few millieV. Something that has been already discussed is the fact that if you have many interacting molecules in a dilute gas, this lower and upper polariton get split with a much larger distance, which is proportional to the square root of n, but then there is an appearance of many dark states in between. However, in all those models, what you assume, and is basically take for granted, is that the ground state of the material, because it's model Hamiltonian, is being unchanged. And this is something important in what will come next. Then basically what we did is apply this theory to prove first that there is an important contribution to the modification of the ground state of molecular systems. And for that, I will show you two cases, and then which is A, for the modification of the density of at the level of the density functional theory, that you can see what is the modification between having one photon in the cavity and no photon, and then you see that the density gets slightly distributed. You have to see the scale, which is very small, it's 10 to the -3, but it still is an effect which is non-negligible. And this modification of the ground state will have implications in few things that will come next. But one of the modifications that is more important, besides the ground state, is the modification of the interaction between excited states of the molecular system. And here, I will take one example that is from the work of Christian, but there are many others in the literature, and this just to highlight the relevance of this molecular interaction mediated by the cavity. And then let's take one example, which is this donor-acceptor by coupling between electromagnetic interaction. And then you all know that between the donor and the acceptor, if you create an excitation in the donor, this excitation decays and creates a virtual excitation in the acceptor. And by these fluctuating dipoles, you couple the donor and the acceptor. And the classical theory, which is dipole-dipole interaction, tells you that the interaction between the donor and the acceptor decays polynomially with the distance between the two molecules. And this is mainly because you have two components, which is basically the transverse part of the field, which decays as with the cube of the distance, and then the longitudinal part of the interaction, which goes as r to the 6, which is dipole-dipole interaction. The question now comes, what happens if you take this system and you put it in the cavity, and you tune the cavity to this excitation between the HOMO and the LUMO of the donor? Can you control the exchange of energy between the system? And then the answer is yes. And in fact, the longitudinal part is something that will decay as normal because it's just classical electrodynamics. But if you see here this figure, just to illustrate the case, if there is no coupling, or the coupling is very small, the transverse part decays with the distance between the two molecules as expected by classical theory. And then once you start turning on the coupling and to the transverse contribution, you realize that this transverse component of the electromagnetic field dominates the interaction and then stays more or less constant over a wide range of interatomic distance. This is quite important because this tells you that the photon is acting again as the glue between this excitation in the donor and the excitation in the effector. Just to give you a flavor that this is not really an artifact of the density functionalization of the interaction between electrons and photons and electrons and matter. There is a nice extension that we've been doing, in particular with the group of Henry Koch and Enrico Ronca, and then thanks to the student Thor that has implemented the coupled cluster theory to describe molecular polaritons. And here there are two aspects of it that prove the previous results, and then in a solid grounds that there is a change of the ground state and the excited states. This is just two cases, which is H2 and HF, which is just one with dipole and the other without dipole, in which you get what you would expect, plus few other features, which is basically the ground state. In this scale, you will see it's not much modified, but then there is the standard splitting between lower and upper polariton of the different excited states in the system. And you can see how the nature of the excited state is being changed from being mainly matter contribution to photonic contribution. And those states are the modifications with respect to the gas-free states, which are the ones that you don't see, or in a few cases you see, which are the red dash curves. And this effect happens both for the hydrogen and for the hydrogen fluoride molecule. However, what I think is really important is that if you make it in another bigger system, which is p neutral aniline, you will see that in the cavity, when it's tuned to the homolumo excitation, you see a change of the electronic density of the molecule in the ground state, which is of the same order of magnitude of 10 to the minus 3 with respect to the molecule outside the cavity. Then this is to give you in a solid ground that there is indeed this modification of the ground state, and then you have a playground to basically either control chemical reactivity, control the interactions of the molecules, both in the ground state and in the excited states. Just going into this idea, we've been discussing this dipole-dipole interaction between molecules in the cavity. And this in an extension, you can do it in a more wide range of different sizes of the molecules, which is dipole-dipole interaction or hydrogen bond type of interaction, which is either van der Waals or hydrogen bond. Let me show you two cases, which I think is illustrative of the power and the need to go beyond some normal functionals. Here I'm comparing for this case, the results in this paper, the case of benzene with water molecule as a function of the distance between the water molecule and the benzene, and the cavity is polarized as along the dipole between the benzene and the water molecule. Then if you take Hartree-Fock and many density functionals, you will get that the system is in most cases unbound. In the gas phase, you get the solution in the coupled cluster single and doubles, which is this small dip, which tells you that the water molecule is bound with the benzene molecule at a distance of around 4 angstroms. However, once you put this molecule in the cavity and the cavity is tuned to the homolumo excitation, you immediately see that this bound state is being removed. Then basically you can control the bonding and anti-bonding nature of the molecule in the cavity by coupling the dipole moment of the complex system to the vacuum fluctuations of the cavity. The same for proton transfer, and this is something which is illustrative of basically the difference between the Hartree-Fock standard change correlation function in an optimized effective potential and the coupled cluster. At the end of the day, you see the need of including this type of higher order correlated methods to describe properly the interaction, but the physics is already captured at a given degree by the functionals that we have in the QEDFT. This was more to illustrate the question of, can you control molecular interactions and can you modify the ground state of a molecular complex in the cavity? And then as you realize, what I did is basically take a single molecule or two molecules. One of the beauties of this system is, and that has been introduced, is the fact of using the collectivity of having n molecules in the cavity which do not overlap and interact weakly among themselves, and then use that as a way to enhance this lower and upper polariton separation and call it that strong light matter coupling. I would like that this concept is still there. There is this, as you saw before, this lower and upper polarity splitting. However, the physics of chemical reactivity is still local in nature. And I think this is really important because what you are trying to address is process in which reactions happen not in a collective manner, but in one-by-one process, in which one molecule undergoes the reaction and then the next. But it's not the fact that the collectivity reacts in a coherent manner, all of them simultaneously. This is a minor but important difference to the concept of this macromolecular complex that many people describe in this polytonic chemistry. But doesn't introduce any contradiction. It allows you to explain the local chemistry of a molecule embedded in a macroscopic environment. Let me build a little bit more on that. And the question is, what do you have? If you have a set of dipoles that are coupled by a photon, you get this lower and upper polariton, and then which is a sort of decay Davis-Cummings models for interacting of n dipoles. And the question is, if we do it in a more ab initio framework, what do we get? Are we able to reproduce this regime, or we have something intermediate? Then whether we go to this macroscopic collectivity, or is more the local nature of the interactions. To do that, what we took is a set of nitrogen 2 molecules, up to maximum of 10 molecules, I illustrate here. And then something which is really important for you to capture is we have a set of n molecules, and I take one of them, doesn't need to be the one in the center, can be anywhere, and I deform it, I perturb it, which is what you do in chemical reactivity. And you want to know what is the modification of the properties of that molecule due to the fact that it's embedded in a big cloud of molecules, and those all interacting with the cavity mode. Okay, this is the figure that you don't see, and you don't need to see it, because here the only thing that you want to get from this is, in the case of the no cavity and the unperturbed chain or the perturbed chain, you see that you have a main peak with the intensity increase with the number of dimers which are not overlapping. And then something I wanted to give your attention to is that once you perturb the molecule in one of the molecules, there is a new peak appearing, which is the defect peak, and that peak is separated from the main peak. Okay, and now the question is, what happens if I do couple that configuration, which is without the cavity, now with the cavity? And that's what I wanted you to go through. Then you get the main peak, which is the excitation of this nitrogen 2 molecule in the cavity. And that one is going to move as I increase the number of molecules in my cavity, which is this collectivity, and goes up, and then also splits with respect to the upper polariton. And then you have this effect. And then there is the middle polariton, which is the one that you will consider in the normal case of the two-level systems interacting via the cavity mode. Then you see basically the effects that you would expect, but there is a major change, is that the nature of the localized state is being perturbed in a different matter by the collectivity of the ensemble. Okay, just to guide you through this plot, there are basically 3 regimes, depending on what is the strength of the electromagnetic coupling, which I write here. It's a perturbative regime in which the interaction is basically dominated by the collectivity of the macroscopic ensemble. Then there is this one in which you have this polaritonic splitting, in which you have the mixing of the upper and the lower polariton, and the appearance of the middle polariton with modification of the nature of it. And then also, don't forget, there is the appearance of and disappearance of strength in the dark states. The dark states become to be more or less in some regime independent of where you are. Then basically, this is what I wanted to tell you, that you have a lower polariton, which is behaving the way you would expect. Then there is the middle polariton, again, coupled to the light. There is a region of extremely interesting dark states, which has been also described by Joel in some of his publications, and then the motion of the upper polariton. But what matters here is that the physics of the lower polariton is, in this case, is linked to the physics of the nitrogen dimer, and this is something which is very important, that you can control the chemical reactivity of this perturbed dimer by the ensemble of all dimers. And this is good because you don't need to be in resonance with the dimer itself that you want to perturb, but with the environment. And this is an environment-mediated chemical enhanced reactivity. It's not a collectivity phenomena, but it's the collectivity of the environment that enhances the reactivity of the molecule, in this case, in the center. And I think this is important because it allows you to bring the standard concept of chemical reactivity that everybody knows in a different framework in which the coupling and the reactivity is described in the same terms, but mediated by the collective mode in which that molecule is embedded. And you can couple two. Okay, this was what I wanted to tell you about molecules, just to get some connection to previous presentations in this series of seminars. And I wanted to move to solids, which will be 2D systems and other variations. And then let me highlight what I wanted to tell you. One aspect is the control of excitons, because will be an exciton in a 2D material is like an electron hole pair, which you have a dipole. And this dipole, sorry?
Oh, sorry. Yeah. We have a question probably related to the previous content. So,
perfect.
Perfect. Matt, you can ask.
Yeah. Hi. So you showed results up to n equals 8, like in the previous slide.
We have.
So what do you expect when you go to n, very, very large, like similar to that relevant in experiments?
Okay, this is a good question. For what I was discussing at this point of the nitrogen 2, which the perturbation, I think the effect will saturate. There is this saturation that you start seeing. Of course, still there will be room for slight modifications. What I wanted to say is that when the number of molecules is big enough, the n-1 molecules that constitute the environment acts as a collective macroscopic system to which you do the coupling and modify this collective state. No? And that one is the one that afterwards couples to the molecule in between and controls his chemical reactivity.
Okay.
I don't know if I answer. It's not the question of having this super radiant or decay-like state. It's not that. It's just that you have this collective mode to which you try to couple, and this one is the one that afterwards dictates the chemical or the local motion of the molecule in the cavity. It's not that all molecules react in unisonous to the perturbation.
Okay, thanks.
But still, you are right, we need to go beyond. And there is something I did not show you because the only effect that I did here is vibration. No? You have the molecule, I expand it, and this will vibrate. This is the only thing I've been trying to control. What you would like to do is this molecule interacting with maybe oxygen or another molecule to undergo a chemical reaction. Then everything I showed you before was not for a chemical reaction, was to modify the dynamics of the perturbed molecule in an ensemble of unperturbed molecules coupled to the cavity. But was to highlight this effect.
Okay, thank you. Yeah, we have another question. So, okay, Pumbe, you can ask.
Okay, so thank you. So this is Franco from Rochester. So I'm curious that when you describe many molecules coupled to cavity, do you have cross-molecule type of dipole self-energy explicitly showing up in your Hamiltonian, say μ1 and μ2, this kind of dipole self-energy? Or
yes, we do include that. And in fact, those are terms that do play a role. All the interactions between molecules which are dipole and beyond dipole in this case, because it's a finite system, are included. The only thing that I have to tell you is we did include for those calculations a single cavity mode. And the cavity mode was treated in the dipole approximation. Then we assume the field is homogeneous in the cavity. No? This is the only assumption that has been made so far. Then the question of how the other cavity modes and the fact that the mode is beyond the dipole has not been included in the description so far.
I see. Thank you.
But the other ones, which is everything that is matter-matter interaction, is included to the highest degree you can, assuming the functional that we use, which is in this case OAP, works. Okay.
I see. Do you see partially cancellation of a partial cancellation between this kind of dipole self-energy mu I mu j to the intermolecular interaction? Because under the perfect cases where you don't have charge overlap between two molecules, they should cancel perfectly.
Yeah, we do. In fact, we see this interference, which is in some cases constructive, but in the case that you were mentioning, will be killing the effect, and then they compensate. Yes.
Okay, that's really interesting. Thank you.
I think this is important, but that was the reason I make the case that I really make one of the molecules distinct from the others. Then this introduces the way to do the coupling. Otherwise, you will end up in the case that you were referring to, because we are in the dilute regime. Still, we are not as dilute as you would like to be, because we are limited in how far we can put the molecules in the first principle calculations. But for all practical purposes, there is no any major splitting due to nitrogen dimers formation.
Thank you.
Thank you.
Okay, thank you. Please continue. And I think that's all of the questions.
Okay, good. Thank you. No, what I wanted to say now is, if you think of dipoles now in the solid state, language will be excitons. No? You just take the 2D systems, you create an electron hole pair, and you will have many excitons living in your 2D material. And this will be the realization of what we were discussing before, of many molecules interacting with the cavity. In this case, will be a density of excitons that you have in your system interacting with the cavity node. And that's what you want to illustrate pictorially here. Then I will address only two aspects, if I have time, is the control of excitons, and then to illustrate something which I found extremely important, which is the first proof that you have a modification of the ground state of a material in a cavity, which has been also addressed in a different regime by Eugene Dembler group in Harvard. Then basically the point here is two, one is on excited state dynamics, and the other is in the ground state. And then I leave you, because I will not have time, to discuss the formation of new quasi-particles, because now you have, polarons, polaritons, and then you can do a combination of what is a polaron and a polariton, and introduce what is a phonoriton, which is a phonon, exciton, photon quasi-particle, which is bound due to the cavity. And then you can think of similar constituents to be created in your cavity, which is quite interesting. Then let me highlight the case of the excitons in a cavity. I took for granted that based on Menon, Binot, and other presentations already, you are familiar with the series, which is basically heterogenic series of excitons in 2D materials in the cavity. And this is just for molybdenum disulfide, in which you have the 1s, which is the dipole allowed, all dipole allowed excitations in your system. Okay, and this is for the first cases for the material without the cavity in the gas phase. Then what we do is we put this material in a cavity in which we embed it with highly insulating polymer media in order to have the frequency of the cavity, which is the length of the cavity tune. And then I am going to show you what is the energy spectrum as a function of the cavity frequency, in this case, the length of the cavity. In the case, this is basically, you will get something which is the phonon dispersion, which is linear. And then what you get is exactly what you would expect. As when the photon dispersion hits one of the dipole allowed excitations, you get the formation of the upper and lower polaritons, and this goes up all the way. Then for the weak coupling regime, you get what you would expect, and is in the perturbative regime. The question is, what happens if you keep increasing the intensity, which is the coupling, and you go to what is a strong coupling regime. The first thing you should notice is that this splitting overlap. This overlapping of the excitations between the A in this case, or A and B, introduce that the appearance of new peaks with oscillator strength, which is not negligible. And then there is a higher splitting at the crossing point. And this oscillator strength survives even beyond the light cone. What those states are. And then what I didn't show before is that those are the bright excitons, but then you have the dark excitons of the molybdenum disulfide. And if you see, those dark excitons become slightly to be activated by the coupling to the cavity. Then this is a quite interesting mechanism, which is also borrowed from atomic physics, which is in double ionized excitations, in which they get oscillator strength in linear response by being close to a single excitation. Then here is the same, you're getting oscillator strength because those dark states become to be close to a bright state, which is the one that is being spelled out due to the upper and lower splitting due to the coupling of the exciton to the cavity mode. This is nice because it allows you to do something which is access in optical response to dark states. And then you can control not only the appearance of the dark state, but the darkness and brightness of the different states in the material. Okay, this is one aspect, but something which is would be interesting is now, instead of having one material, you can play with the materials and try to look for the control of the inter and intralayer excitons. Let me give you the cartoon. This is two to the materials. What you have is the first is the exciton of the lower one. Then when the exciton is localized on the bottom of the 2D, then on the upper, and then they have different energies. But when the cavity gets in resonance to the middle part, with this is the splitting of the two polaritons, then you get the exciton being excited automatically on both materials. And then, of course, you can move it to the right and exchange it. The question is, what are the implications of this in a real material? Then let's take, in this case, is tungsten and molybdenum disulfide, and you have the intralayer exciton and the interlayer exciton. The order of energies in reality in the experiments is this one. You have the intra below and the inter above in energy. Then the question is, what can we do when we put these materials in the cavity? And I do exactly the same thing I showed you before. I put it for a weak coupling and a strong coupling regime. In the weak coupling regime, we get what expected is that those modes get slightly split, as we wrote in the cartoon before. And then this splitting is proportional to just the coupling constant, which is proportional to A0. However, when the splitting is large, then you start to get mixed character, an appearance of, again, new states. Let me highlight what is happening. What is happening is that before you were having these intralayer states here, and then all of a sudden, the intralayer state of the upper to the material goes up in energy, and then the interlayer state goes in the middle. Then in this way, you can, by coupling to the cavity, decide the energy ordering of inter and intralayer states. In fact, if you were going to the ultra strong, which is something which is difficult to reach, this could be even the lowest excited state of the material.
Professor, yeah, sorry to interrupt. I have a question here.
Perfect, then.
Okay, Joel, you can.
Okay, Joel.
I have a question about when you talk about brightening the dark exciton transitions. So does this only happen when you have counter-rotating terms? Because I believe if you just remain with the rotating wave approximation, those effects do not happen. And
I think you are completely right. Here we did include both the counter-rotating terms, and on top we did include the diamagnetic contribution, which is this electron self-polarization that has some effects to make the calculations stable. But you are perfectly right. You need to have this counter-rotating in order to transfer oscillator strength to the dark states.
Okay, and I guess then the next question then very quickly that I would like to ask you is, in these 2D material systems, do I need to worry about dark states? Because normally when I talk to people who do solid state, they talk about dark states as like the K very large, you know, the polaritons at very large K, which are pretty much parked at the same exciton transitions, but at every different, at intermediate K points, are there dark states? My understanding is that if there's some finite thickness of the material, there should be, but I don't really understand this very well.
Okay, now your question has two sides. It depends on which is the material. Some of those 2D materials, the dark states are very close to the bright ones on the bottom. And then in those cases, they do play a role in controlling the dynamics. In the cases that you were describing, you're right, which is they tend to play a little bit, not role, because are at high Q. But with the ones that we are looking at are really states that they get extremely close to the bright. And in some of these 2D materials, there are cases in which if the thickness is big enough, the bottom of the exciton series is dark. What you have in these organic polymers, no? When you want to control the light emission, you want to quench the dark states if you want to have light emission, because otherwise they don't emit, then fluoresce. In this case, it's more to control them, because those dark states allows you to control energy transfer between layers when you have heterostructures.
Yes. Thank you very much.
But right, it's a game. Then the question here was more not to come up with something which is useful, but to make the dark states bright, and then to see whether they do play a role. And if we have them bright and then we can see them, they might have also implications in what we discussed in the previous part, which is visualizing the role of the dark states in these macromolecular polaritons, which is something that, by the way, you've been working on in the past in some of these molecular crystals.
Thank you very much.
Thank you, Joel.
Okay, thank you. Please continue.
Yeah, now comes the problem to go to the previous point. Okay, then this was for them to prove that we can control the energy spacing. And then here is where I'm getting towards the end, but then stop me anytime that is needed. Then don't worry. I just want to give you one case, because everything I discuss now is about excited state properties, which is what you would expect. If you have a dipole and it's excited, then this will emit a photon. The photon will couple to the next material, and then you have this intertwined communication between the system by emitting and absorbing real photons. The question is, can I do something similar, which is modifying the material's properties, but exchanging virtual photons, which is this cavity quantum fluctuations? This is the question that we want to address. We already know the answer, that the answer is that in molecular systems we do, because we show you even with the coupled cluster calculations that Enrico and Henrik did. Then the question is, can we do the same for solids? And then here there is a huge debate in the community, because in all the things that are related to decay-like and variations model, this is not included. And then it's assumed it's not happening. But let me tell you something that I think is important for you to take home, is all those effects that being discussed in the past about 2-level or n-level systems coupled to a bosonic excitation, everything is harmonic in many aspects, which is a 2-level system coupling to harmonic potential. In those situations, there is no relevant modification of the ground state. In order to get modification of the ground state, and this is the key, you have to get non-linearities in the light matter coupling. And this is what you get in the calculation of molecular systems. There are plenty of non-linearities coming from the electron-electron interactions, plus the electron-photon interactions. And on top, if you want, you can add the non-linearities from the photon-electron interaction. But the non-linearities in the material are the ones that dictate that you can control the ground state. Otherwise, it's not possible. Okay, then let me show you one case, and at least this is what I want to finish. And then some of you are familiar. If not, I give you a fast overview with strontium titanate, which is widely studied and understood. Strontium titanate is in the ground state is a paraelectric material that, if you drive it with ultra strong terahertz pulses, which is with the exciting a phonon, you can make it ferroelectric or transient ferroelectric. Okay, and there are different papers in which they demonstrate the ferroelectricity, at least the transient ferroelectricity in those systems. Then the argument is the following, and then you will understand why I'm interested in this, which is very similar to what we were discussing before. In a paraelectric, what you have is the paraelectric, you have domains in your system that each domain has its own dipole, and this dipole is randomly distributed all over the sample, and on average, you get zero electric moment, which is basically the argument of calling it uncorrelated dipoles. And what you want to do is, if you come with a strong light, you want to find a transition in which you align those dipoles. And this is basically what you will call the quantum paraelectric or paraelectric to ferroelectric transition. The open question is, can we do that without the field and in the cavity? Okay, and that's the cartoon that I want to highlight. And then we already know the ingredients. The ingredients is this thing, that what we want to do is we want to go from this uncorrelated dipole to a set of aligned dipoles around the polarization of the field in the cavity. In this case, is in this direction. And to reach that, we need to know which are the main ingredients that dictates the paraelectric to ferroelectric transition. And this is quite well known, that there is basically two lattice distortion, which is the fact that you go from the tetragonal to a cubic phase with rotation of the octahedras plus the displacement of the titanium and oxygen atom in each of the octahedra, which is the ferroelectric soft mode. You don't need to know more because basically at low temperatures is tetragonal, at high temperatures goes to the cubic phase. In both cases, in this case is quantum paraelectric, in the cubic phase is paraelectric. And then if you apply strain or pressure, you can make the system ferroelectric. But at zero pressure, the system goes from para to paraelectric. Is when you apply strain or the perturbations that you make it ferroelectric. And that's what is happening with light. We want to do similar things with the cavity. And then the argument is extremely simple. What you want is you have the cavity. You want to couple the cavity mode to this ferroelectric transition in a way that the system deforms, and this deformation drives the paraelectric to ferroelectric transition. This is the cartoon in which we are going to have a thin film of then separated from the electrodes from a polymer. This allows us to control the coupling because then we can increase the thick of the polymer and then be in the terahertz regime because we are going to work in the terahertz cavities, and then couple to the different modes of the STO. And here there are two modes that are extremely important. It's the titanium and oxygen separation, plus the fact that when you move the two atoms, the lattice elongates and goes to the tetragonal phase. If those are the fields, then let me give you what you get, because this was more for the summary of the talk, is if you are at not coupling, you get what you expected is that the material is a quantum paraelectric, which is dictated by this double well position, in which the system wants to be ferro with polarization in this direction or polarization in the opposite, but on average get zero, and then give this is a quantum solution of the problem, which give you a zero polarization of the system with two lobes. And as you increase the coupling, what happens is that the barrier in between increase, and then the density is localized on either one or the other well, which is a linear combination because both are energetically degenerate. Then you have to be on the right or on the left, but then there is a barrier. There is basically no overlap in between. And then you went from the quantum paraelectric to the ferroelectric transition. And that's something which is, I think, is important for you to know, that to reach this transition, the only thing you need to do is to increase the electromagnetic coupling. And just to make the story short, what is happening here is that for many frequencies, there is a regime which is from 1 to 10 terahertz in which this modification of the ground state happens. Let me show it to you, which is the cartoon of the physics. Is you start from the quantum paraelectric, I keep increasing the coupling, then I localize, which is a dynamical localization of the two wave packets in one of the well or the other. And this dynamical localization introduces the ferroelectricity. If now I increase temperature, I delocalize the system, and then I go back to paraelectric. Then there are two types of fluctuations that you need to overcome with the cavity. One is the fluctuation due to the quantum well transition, which is a quantum fluctuation in the ferroelectricity, and the other is the quantum fluctuations from the thermal motion. And with this game, you have something which is new, and I think is a photo phase diagram for STO, in which you can go, this is a schematic, then don't pay too much attention to the lines. In the tetragonal phase, you can go from a quantum paraelectric to a paraelectric to a ferroelectric solution. And this is quite nice because it allows you to control both as a function of temperature, as a function of coupling, the nature of the ground state of the material. Okay, and this is, in my opinion, one of the first cases in which the intrinsic non-linearities of the coupling allows you to have this as a phase in which you only couple to quantum fluctuations and you don't need to drive the system. Okay, and then just to end, this was coupling to light in the normal mode. Then now you might think something that has been worked is chiral cavities, in which I have Faraday rotating mirrors. And then instead of having a mode that is polarized along the axis of the cavity, which is, let me give you the hint, this is the linear polarization of the normal cavity, this is the cavity mode. I can have it depending on whether this is a Faraday mirror or another type of mirror. You can have an helical mode, or something which I think is more important is a chiral mode. A chiral mode is a mode in which time reversal symmetry is broken. You have either left-handed or right-handed modes, and in each plane you can get this time reversal symmetry breaking state, which is the mode. I want to remind you that this is local symmetry breaking in one plane. The whole system, including the mirrors, does not break time reversal symmetry. This is important for you. We are not breaking, it's just a local modification of the time reversal symmetry inside the cavity once the mirrors are not considered. And if you take that into account, this was done also in that reference, then basically what you can induce is if you put graphene, just to illustrate the physics, which graphene is a Dirac semi-metal, by coupling to a cavity which has chiral nature, you will open the gap, and the gap will be proportional to the coupling. Okay, then I think this is it's already 1 hour. I think I will not have time to address what I told you, but I told you at the beginning I was not going to be able to do it. Then let me give you 2 slides to motivate what is the interest. I told you about excitons, I told you about 2D materials, and I told you about cavities. What is the fun of working with 2D systems? Is that now you can do, on top of having the 2D, you can start twisting them. And by twisting, and then now you have to believe me, what you do is by slightly modifying the angle and the nature of the material, you can generate different types of low energy Hamiltonians, which will be a Hubbard-like triangular lattice in which you can control the doping. You can have hexagonal lattice, which is the normal. You can have one-dimensional structures or cubic lattices. And this allows you to mimic in a material the Hamiltonians that has been studied for many years in the condensed matter community as correlated materials. And this goes from Kagome lattices, in which you can get exotic superconducting states, to all these Kitaev models for spin liquids, to Majorana modes at the border. Then you can have something which is beam proof already, which is this moire type of excitons that will be controlled if you put them in the cavity. And then you can have magnetisms of the quantum magnets in localized arrays of your moire structure. And all that is the playground I wanted to tell you, because then you have new systems. You can get the new phenomena because you can realize the Hamiltonians that has not been realized so far. Then you can engineer the interactions because then you have the coupling to the light, and then eventually you can have applications. And then this was the cartoon in which you have this feedback between the 2D twisting and the interaction. And I want you to keep something which you might think, why I am telling you that, if the energy scales are very small. In fact, because of that. The interaction between layers is of the order of millieV, but the interaction between the cavity mode and the matter is of the order of millieV. Then you are in a regime in which electron-electron and electron-photon interactions and electron-phonon interactions are all in the same range. And this is the ideal platform to get correlated materials. And then you can really now turn the knob and then try to estimate whether the different states can be realized, from spin liquid to D-wave superconductivity, okay, and you name it. This is the nice thing, and then we just got perspective in nature physics is describing all different materials that you can generate outside the cavity, and then now you can play around with the different interactions inside the cavity. Then I am done. I will not show you that. And then with that, I hope I convince you that we have created a framework, a theoretical framework, which has two legs, one based on density functional theory, the other more on quantum chemistry, that allows you to treat light matter interactions at different levels. This opens two new fields, which is quantum electrodynamics chemistry or quantum electrodynamics materials, in which you can modify chemical landscapes, which is the ground state and the excited state, and in materials that you can really change the phenomenology, and in particular the properties of the materials, by coupling to these quantum fluctuations. And then you can now call out of this thing that I told you at the beginning, which is the photon, phonon, and dressing due to the cavity mode. And then you get this 70 type of polaritons playing role in the new states of matter that you can synthesize. And with that, I thank you for your attention and thank all the people in the group that is responsible for what I told you up to now. Okay, thank you.
Okay, thank you. Thank you. It's a very interesting talk. We have a couple of questions, so I will. You know how you can speak?
Yeah, hi. I have a question about the section where you put a 2D material inside a cavity.
Yeah.
So in that you mentioned that you mentioned a particular energy when the exciton is in the bottom layer and when the exciton is in the top layer.
Yeah.
I thought because of symmetry that should be equal, right? And that the two that you were mentioning were probably linear combinations of them.
No, okay, this is not equal because I was taking two different heterostructures. It was molybdenum disulfide and tungsten disulfide, and they have different energies. Then
you're taking two different heterostructures.
Yeah. Okay. In the case that you are talking about, which is a bilayer, homo bilayer, then you will have this hybridization, which will be a linear combination of bonding and anti-bonding excitonic states. And this is what allows you to create this moire lattice of excitons in these homo bilayer systems. But in that case was a hetero bilayer, just to illustrate that you can discuss between intra and interlayer excitons. And this was done because there are very nice papers, experimental papers, in which they look to extremely long-lived interlayer excitons due to the coupling to the cavity or other external excitations. And that's something you are interested in having, because then you can have the electron and the hole living in two lattices.
Okay, thank you.
Thank you.
So next question. Oh, well.
Okay.
Sorry, a very interesting talk, Angel. So I have very quick two questions. So the first one is, besides temperature dependence, is there an easy way to distinguish between the quantum paraelectric phase and the thermal paraelectric phase?
Good question. This is probably, you have been following the literature. This is an open question. The main fingerprint of the quantum paraelectricity so far is the fact that the frequency of the ferroelectric soft mode, when you do Raman spectroscopy, but has to be done as a function of temperature, goes down, 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 gets soft, soft, and all of a sudden flatten and goes to 0.5, okay? And terahertz. This 0.5 terahertz, which is the stability of the ferroelectric soft mode, could not happen if you did have a paraelectric. In a random paraelectric, that mode will go to 0. Then this is so far the real fingerprint of this quantum paraelectric phase.
I see, so spectroscopic.
And the beauty is, and then this is to add, if you did not have the quantum paraelectric, you will not be able to induce the ferroelectric transition. This is something which is something to mention, because this is the non-linearity that you need to have for the cavity to allow you to go from the para to the ferro without putting a strain. No? In reality, when you put the STO in the cavity, the interaction between the STO and the matrix and the STO and the mirrors might introduce a little bit of strain. And that will be another non-linearity that opens the door to induce the ferroelectric transition. But assuming this effect is minor or negligible, because you isolate the STO as much as you can, then the effect of having the para to ferroelectric is possible because the potential energy surface that I show you is really non-parabolic, is beyond the harmonic. And the non-linearity is important.
Thank you. I see. And just for a follow-up to your last part of your talk, can you explain again, how do you create the chirality in these cavities? For example, with graphene, like, is this like a cavity made of magnetoptical materials, or what?
What you do? Okay, the point is that, and this is a good question. Okay, let me show it to you. This helical mode of the cavity is trivial. Okay, then you can have a Faraday rotated mirror, and then with two of those, you can play around, and then immediately you can see. Then it's not a major thing. But this one you are not interested in, because this one at each cut satisfies time reversal symmetry. Then you are not breaking the symmetry. You have something which is nice because you have angular momentum, but you don't break the time reversal symmetry. It has other implications if you want to have DD transitions and other type of phenomena that you might be interested in. In this one, in which on each cut you can have left-handed and right-handed, you need to have activated metamaterials mirrors.
Yes.
And this is true. Or you can have what is these strongly birefringent mirrors. That basically what you do is you have this. Okay, one of the cases will be sugar, but sugar will not work because will destroy your material. But if you come with sugar, you come with light, the reflection of left-handed and right-handed are extremely different and are split. Then sugar by construction will create a cavity in which the lowest polarity is left-handed and the next one is right-handed. However, here what I would like to do is to have all modes left-handed or all modes right-handed. And for that, you need to have an activated magnetic metamaterial. But to answer another question, so far, they have not been synthesized in this structure, no? What you can use is these antiferromagnetic superconductors on the basement, and then you can use that to create this split of left and right. And as a practical thing, acts very similar to what I'm telling you. And will open the gap in graphene.
Thank you. Yeah.
Oh, you do the torus, but the torus is the trivial case that has not been. Right.
Yeah.
You have, we wrote this with Jerome Feitz, which is an ETH, and he's really an expert in all these cavities, and he's presently trying. And this configuration of the torus is the one in which you might be easier because you can do it with optical fibers. And then you can have this regime in which you have this time symmetry breaking state. And then you can think of putting superconductors and then address Goldstone modes and other type of Higgs modes if you are interested. But we didn't do anything there.
Okay, thank you. Yeah, so due to the time limit, let's put an end to today's webinar. So Professor can stop sharing and I will show the send off slide for next webinar.
Okay.
Yeah, thanks. Okay. Yeah, thank you, Professor Rubio. It's for a very interesting talk. So today we have over 100 attendees joining us for this webinar, and we hope we could continue in the future. So we really appreciate your contributions to our webinar series, and like to have more communications in the future. So for next webinar, Professor Henry Koch will give us a talk entitled Novel Wave Function Method in Cavity Quantum Chemistry. So still be on next Wednesday, 9 a.m. Pacific Standard Time, and don't forget to register. So thank you, and see you next Wednesday. Bye-bye.
Thank you.